What's up guys, Mike here, and welcome to the second video of our new Vesc series tutorial video. So in the last video, we went over all the physical connections of our speed controllers, what all the ports do, where you plug things in. And now today we're going to start actually programming the speed controller so you can get your board up and running. Inside of here, it might seem really intimidating. There's cables and black spaghetti everywhere. It's fine, we'll get through it all together. So to start off, I usually like to connect all my phase connections. So that is our main 3 wires of our motor. So you can kind of see in here that we've got kind of the right and the left. So we'll go through here. So your right motor cables will go to your right ESC phase cables. So you don't want to cross. We want to keep everything as far as we can, as standard as we possibly can. Now, you might notice on your motors, in this case, they're all black, but in your case, they might actually have color. So if that's the case, don't worry about it. Color at this point does not matter. If you would like to plug them in a certain sequential order to kind of keep track of everything, you absolutely can, but it does not matter for what we're doing. So just plug them in. As long as all your right cables go to the right, all your left cables go to the left, you'll be good. So continuing on, let's actually get these things plugged in. So we got phase wire 1 and 2 and 3. Good. And now we'll move on to the other side here. We'll do some untangling really quick. And all right. And we're gonna do this in real time, guys. I wanna make sure that everybody has no actual additional questions. I don't wanna skip over anything. So again, we are just gonna plug everything in. Boom. Okay. So now we've got 2 sections. We've got our left and our right. And now we've got our motor sensor cable. So these are also important. Now, again, you want to make sure you're plugging them in on the correct side. So our first cable will go here in our first hall sensor port there on the left. And now we will do our right motor here in the second hall sensor port on the right. Okay, we're making good progress. Now that our motors are done, we will start working our way from the backside here to the front. So here is our power button. So our power button is kind of clicky over here. It's located right here, and the cables wrap over here. 3 pins to 3 pins. Now again, we went through all these ports in the previous video, so if you missed that, you should definitely go check that out. Now moving on from your power button, we'll want to make sure that we're plugging in our Bluetooth module here. We always put the Bluetooth module right next to our power button just to keep everything standardized here in the shop. Technically, you could do them either way, but if you do your Bluetooth here, it makes things a little easier later when we're talking about the programming side of things. So I will plug in our Bluetooth connection here. It's a little hard to see, but there we go, our second port. Now, one of the last things we'll have to plug in is our receiver. Again, the receiver technically could go up here, but we're gonna put it in our last connection here. So that is populating our last UART port there. Now this last port here, we don't need that unless we are doing a 4-wheel drive board, which in this case is just 2-wheel drive, so we're good to go. Now the last thing we want to plug in is the power, which actually you can see here that I actually locked this cable in place. So I'm going to unplug this and move this cable and plug it back in. We want to make sure that we're keeping an eye on cable management. Now this board was an existing prototype Endurance 2.0, so cables are kind of wonky in here. We kind of threw it together to test her, but most of these cables are actually pretty well cable managed-ish. I think at the end we would go through and zip tie some connections together. Okay, but in this case, in this way, we are all ready to go. So now at this point, we are going to plug in our power. Now if you heard that, that would be a little bit of a spark. These are anti-spark connections. However, when you first plug in your ESC to your battery, you might hear that little bit of a pop. It's pretty much high voltage going into no voltage, so it's just going to give you a little sound. It shouldn't be anything major, but don't freak out if you do hear that. Okay, now we've got all that, and at this point, your board should power on. So I'm just going to push the power button back here, and the D100 you actually have to hold a little bit. Okay, so now you can see we've got lights going, and we're on. So cool. So now at this point, we can hop into Vesc tools. So at this point, we do need to plug this thing in via USB. Now, technically, you could program this via Bluetooth, but we really don't suggest it. It's not very reliable. Sometimes your settings seem like they're being saved, but they're really not. So 100% you should be using a PC or Mac, and really you should be using a PC if you can. The Vesc tool for Mac is an adapted version, so it's also not the most reliable, though we've had really good luck with it, so we're gonna rock that for this video. Another thing you wanna keep an eye on, we have a super long USB cable. We know this cable works, but the length of cable, believe it or not, does matter sometimes. So you wanna make sure that you're trying to use on the shorter side of the cable. But another thing is, it needs to have data. So again, we've tested this cable, we know it works, so we are gonna plug this here right into the first USB port next to the power switch connection. So boom, there we go. Okay, so now we've got that, the board's on, we're ready to start programming. So we're gonna hop over into the computer here. And the first thing we're gonna do is, we've already got Vesc tool opened up here. I always just come down here and hit auto connect. And this works like 99% of the time. So we're good to go. Now the first thing we want to do is nothing to do with firmware. So the thing is, a lot of times when you connect your speed controller, whether it be on your phone or whether it be on the Vesc tool, it'll pop up a message, something like, hey, your firmware is old, it mostly updated but kind of old, updated to get the latest features. We do not want to update any sort of firmware. The firmware that we ship on our speed controllers is tried and true. There are really almost no features that are added in different updated versions of the firmware. So you really don't need to update it. And if you do update it and you don't use the right software or the right firmware version, it can definitely brick your speed controller. So don't update anything. And if you absolutely must, you have to use the custom firmware that MakerX provides, not the built-in stuff on the Vesc tool. So keep that in mind. I would just say, do not update. There's no reason to, we don't, and everything works really well for us. So just leave the firmware as is. So for now, here on the Vesc tool, we're just gonna skip this firmware. Again, if it asks us, we're going to ignore it. The next thing in here is, actually, we're just gonna go back to the welcome in Wizards. We're gonna start here, and we'll do setup motors FOC. Low default parameters, we usually click no. It doesn't really matter. We're about to change everything anyways. But here we go. What are you setting up? We're setting up an eSCAPE. So that's what we're gonna hit. We'll hit next. Now this is something that people get confused on. We're using medium outrunner motors. Now they do show pictures, but it is kind of hard to see what the scale is. But we're doing medium outrunner. Anything larger can actually hurt your speed controller using the wrong settings. So we're using an outrunner motor because the cans are on the outside. We're gonna hit next. See, it's right here. Warning, choosing a significantly too large motor for detection is likely to destroy the motor during detection. So that right there. So just click medium. All all electric skateboard motors right now in today, 2024, they're all medium. So we'll just go medium, we'll hit okay. We'll hit yes there. All right, so now here's stuff that we usually do fill in, but it doesn't really change anything as far as the way that your ESC runs. All it really does is it helps the Vesc app give you real-time data, but it won't actually mess your board up or anything. But we'll fill this stuff in anyway. The Endurance 2.0 has a 14S battery in it with a battery capacity. Actually, it's already filled in for me. It must have been from last time we actually programmed something. 33.6 amp hours, which the way that we get that math is here. I actually could probably show you a top-down calculation here. So the way that we get that is each cell has 4,200 milliamp hours or 4.2 amp hours times how many cells do we have in parallel. In this case, this is a 14S 8P, so we're going to times 8, and that gets us 33.6 amp hours. So that's what we're going to input here on the Vesc side. So 33.6, again, doesn't really matter, but we're going to do it anyways. We'll hit next. You've not specified battery current limits. That's true because it hasn't let us do that yet, but okay, we'll hit okay, and now we're going to continue on. So again, you don't really have to do this unless you want the Vesc app to have correct data, so we'll do it anyways. In this case, this board is a 16T and for our motor pulleys, and on our wheel side, what is a 6-inch? This will be a 58T wheel pulley, and then our wheel diameter in this case is 150 millimeters. And then motor poles, unless your motor manufacturer explicitly says that it's not 14, it's going to be 14. So if you're asked for some reason motor pole pairs, it would be 7 or 14 total motor poles. So, okay, we got that. At this point, we're going to start seeing and hearing crazy things come from the board. Do not stress out, but we just do need to make sure that our motors can freely spin. Otherwise, your board will take off on you. So my board is propped up on some foam blocks, so they can spin freely, no problem. Okay, so now we're gonna hit run detection. And it says this is gonna spin up all motors, make sure nothing is in the way, and then we're gonna detect all motors over CAN bus because we do have 2 motors. So we're gonna hit OK. And again, you're going to hear some sounds at this point. So, and you'll see the motors start spinning. Okay. Woo. All right, there we go. So now we'll see front motor here, back motor here. At this point, we are collecting data, or the Vesc tool is collecting data. Cool. Okay. So now it's going to take all the data it just learned. It's actually going to do one more calculation here. The motors will jitter a little bit. And then it's going to dump all that information into Vesc tool for us so we don't have to come up with it on our own. Here we go. Processing. And you can see in the bottom right-hand corner, it's adding things. Okay, success. Here we go. Now, these are the couple things you want to make sure that we're looking for, right? So, sensors, Hall sensors. Now, if this shows up sensorless, for whatever reason, we need to redo it. So, we've got Hall sensors here on one, Hall sensors here on the other, and now we're also looking at what the amperage is being pulled at. Now, these are the nice reacher motors here. So, the amperage is quite high on these, and this is what they detect at. So, they're detecting at about 88 amps each, which is typical for a detection. So, everything else looks good. Now, the main things you want to look at: motor current, are they coming through about the same-ish? And then also, are the Hall sensors coming in? Yes. These also have a temperature sensor, which both of them are coming in as true. So that's cool. So we can hit OK on that. So now in this case, what we're doing here is that we were trying to tell the motors which direction they should spin. So I'm going to click over here and I'm going to hit forward. And then when I click it, we'll cut over to the motors here and we'll see which direction they spin. So I'm going to hit forward, back here, and that is spinning in the incorrect direction. Let me try it again. That's incorrect. So I'm going to just uncheck inverted and I'm going to hit forward again, and now it's spinning in the correct direction. I'm going to do the same thing for the bottom one, and that is spinning in the correct direction. So we'll leave that one as inverted here. So in the software here, one's inverted, one's not. That's fine. As long as your actual wheels are spinning the correct direction, we're good. So now I'll hit finish. Now in this case, we're very, very close to being done on the motor side of things. So we're just going to check a few things. So we're not done though. So detection is just the first section. So next we're going to move on to our current hat. And now remember, there are 2 motors and there's going to be 2 sets of settings. So down here on the left-hand side, we see our CAN devices. We've got our local side and we've got our ID number 100. So local is the side that we're physically plugged into, or where the Bluetooth module is physically plugged in if you are accessing via Bluetooth. So because we're on USB, local side is taking care of this back side towards me here. So here's what we need to do. At this point, we need to start inputting in our information. Now, where your motors detect at is a good starting point. However, these reacher motors, we know we can push them much higher. So what do we usually actually put these in? 120? Okay, so we're putting in these in at 120. So that's what we do for our boards here. Again, if you're using different motors, you're gonna wanna contact the manufacturer and find out what you could reasonably push these to. Okay, so 120 amps here, negative 120 amps there. And okay, now this is the next one, battery current max. There's a little bit of math to be done here as well. So I will pull out the handy dandy calculator out. Okay, so the math that we're gonna do here is based on our battery's capabilities. Now, all MBoards battery packs are not limited by any sort of BMS on discharge. They're only being used for charging. So we have full capabilities of this battery pack. Again, this is a 14S8P P42A pack. Now the way that we figure out what we should put in for the battery current max is how many cells we have in parallel. We have 8 of those, right? Now we're gonna multiply this by the rated continuous discharge of the particular brand of cell we have in here. Now the P42A, the datasheet claims 45 amps. Now you guys can argue whether or not we should actually run this at 45 amps or not. We do, and it's fine. The cells are very, very capable. If you'd like to be more conservative, you can drop it down to 35, you could drop it down to whatever you feel comfortable. But in this case, we're gonna go 8 cells in parallel times 45, and that gives this pack a total of 360 possible amps to be drawn out of this thing. But remember, we are only programming one side of the motor, so it's going to draw that much power out by itself. So what we need to do now is take this number and divide this by how many motors we have, which is 2. So that's 180 motor amps. Now again, or 180 battery amps. So the math would say that the battery can push 180 amps per side. However, the hardware of the speed controller says different. Now the hardware of the speed controller says that it can handle 100 amps per side. So we do have to go down to the least common, or the least spec hardware. In this case would be this actual speed controller, which 200 total battery amps from a speed controller is very, very good. So don't be upset that you can't utilize your full power here. So we're actually going to go back to our software here, and we're going to change this to 100. Now the reason why you need to check this is because if you had a 12S4P that was capable of 180 total amps, your bottleneck would actually then be your battery, not your speed controller. In this case, our bottleneck is our speed controller. So we're gonna drop that to 100. Now the way that we find our regen is we're taking just pretty much a standard charge rate, right? So the standard charge rate for a single cell here is 4.2 amps. It is a coincidence that it's the same as the full charge voltage and also the capacity. 4.2 is not a normal, it's not normal for all those three to link up like that. But 4.2 amps is a standard charge rate. We're going to multiply that by how many cells we have in parallel, which is 8, meaning we can charge this thing at 33.6 amps standard. Again, we're never gonna just stick a 30 amp charger in this thing. That's just totally unnecessary. But then we're gonna hit divided by 2 because we have 2 motors. Now we've got 16.8. So now we're gonna go over here and we're going to go negative 16.8. Again, though, these cells are actually capable of fast charging much faster. Again, it's up to you guys to read the data sheets for the particular cells that you guys are using and make kind of a more or less educated decision. We use 16.8, works well for us. We like the braking power that it provides, so we're good there. Okay, so now that we've got all this information and we've looked at our motor current max based on the manufacturer's recommendations, we have done the battery current max based on the cell recommendations, and also comparing that to the ESC recommendations, which is why we got to 100. And then negative 16.8 is based on our battery's standard charge rate divided by 2. So that's how we got all our numbers. Now once this page is done, we do have to remember every time we do a page, we need to come over here to the right-hand corner and we need to write motor configuration, which is the N with the down arrow. We're gonna write that, bottom right-hand corner, it does say that it's updated, and now we're going to move on. Okay, so now we need to figure out where we'd like our speed controller to cut our battery off. Again, we don't have a BMS that's controlling discharge. Number of reasons for this, but one reason is we believe that BMSs that do monitor discharge have a higher % chance of launching people when they cut off. If you have a peak amp pull, they like to shut the battery off, which is not very good. So in this case, we don't have any protections for voltage for over discharging your battery. So we do need to tell the ESC to keep an eye on the voltage and to stop working at a certain voltage. So the way that we find this now, bring the calculator back out, we need to decide what our cutoff voltages are per cell in series. So this is a 14S battery pack. So what we're doing is trying to figure out where we would like to cut these cells off individually. So in this case, we're taking the number of cells that we have in series, multiplying it by what we like to start our cutoff at, which is 3.05 volts per cell, which is 42.7. So we'll come over here, voltage cutoff start, 42.7 volts, 42.7 volts. And now our cutoff, again, you guys can argue about this in the comments down below. We run ours down to 2.8 volts per cell. And we have had great experience with the P42As doing this. So again, it might be a touch lower than what you guys might want to do. You guys might want to do 2.9, 3.0, you guys can decide, but that's what we run. And we're gonna multiply that by how many cells we have in series, which is 14. And that gets us 39.2 volts. So we're gonna come back over here, 39.2 volts. And we're going to, again, write motor configuration. And you'll know that it worked because we're down in the bottom right-hand corner and it'll give us a notification. Okay, now we're gonna move on. RPM, we don't mess with this. The max ERPM is dropped in by the manufacturer of the ESC. Don't have to mess with that. Wattage, don't have to mess with this. Now on to the temperature tab. Now you can skip this tab. The stock temperatures will work for you. If you live in a warmer climate or you wanna push your hardware a little bit harder or longer, you can increase these temps, but just keep in mind that the hotter you make this, the chances of burning your stuff out is much, much higher. So just keep an eye on that. But you can increase these to get your hardware to run a little bit hotter if you want to. BMS, we don't have anything connected directly for BMS. We can skip this. And under advanced, I don't think we actually added anything in here, right? Nope, we're good here. So advanced is good. Now again, just to do it one more time, we're going to save our motor configuration. You'll know that in the bottom right-hand corner that it's saved. And guess what now? We get to do all of this a second time. So we're gonna go down here, and from the local section, we're gonna go down to the second one, which means we're gonna hop over the ESC. We're gonna hop over to the second side now. So now all the data we just put in, we're gonna do it all again. So I'm gonna run through this really quick so we know all the numbers. You can rewind if you want me to really explain it all again. But I'm just gonna run through here and put all the information in we just did. So 120, negative 120, battery current 100, negative 16.8. And also I'm gonna save my work as I go. Voltage, 39.2, 42.7. Good. Save my work. RPM, wattage, temperature, BMS, advanced. Okay, we're all good there. So we're gonna save that. And that is it for the motor section. So that is how we find our numbers, how we input them into the ESC. And at this point, now the next thing we have to do is the app setting. So that is where most of the chaos breaks out with our customers. So we'll cover that in the next video. So if you haven't already, hit the subscribe button so you don't never miss any of our new tutorials. So that should cover all the motor settings, getting your motors running. And now again, in the next video, we'll do all the app settings and actually get your remote to trigger the motors to actually spin. There are a handful of things we need to do there. So we'll do that in its own video. So keep an eye out for that, and we will see you in the next one. See ya.